Okay, there are two main types of circuits, and they are series and parallel. And in a series circuit, there is only one path for electrons to flow. Now, that means that there are no junctions. There are no places where the electrons can reach a point and then choose to go another way. They have to go one direction all the way through. Whereas in a parallel circuit, there's more than one path for electrons to flow. And this means that we have junctions. So it contains junctions. So let's look at a couple of diagrams that show this. And the first one is a series circuit. So this is a series circuit. We have our power supply, our voltage. We have our three resistors, and they are in series, one after another. So when the electrons flow through here, they move through the circuit, and each electron has to go through each resistor. There's no other choices. So every electron goes through. Now, what happens if we have lamps or some other kind of appliance in here and it burns out? Well, if this burns out, electrons can't get from here to here, so these will also not work. So the common question that you see are holiday lights or Christmas lights. Sometimes they're wired in series, and it's super annoying because if one bulb burns out, all of the other bulbs burn out. Now, more modern day Christmas tree lights are wired in parallel, so there's multiple ways for the electrons to flow, so that one of the light bulbs burns out, the other ones stay lit. So that would be a parallel circuit. So a parallel circuit, we have junctions. We have points of splitting where electrons can go different ways. So if we look at this, we could have an electron come down. It has a choice. It can go this way, or it can go down to here, and then it has another choice. It can go this way, or it can go this way. So the electrons are going to mostly travel through the lowest resistor. So if we had, let's say, 5 ohms, 1 ohm, and 3 ohms, electrons will go through all three, but the most of them will go through the 1 ohm resistor, meaning that the current will be highest here and the current will be lowest here. Now, there are certain rules that apply to series circuits, and the first rule is this. V total, and they don't write T on the reference table, but I think they should. It means total, and that's equal to the sum of all the voltages in the resistors. So VT is equal to V1 plus V2 plus V3, and we might have more, so they write plus dot dot dot. If it was only 2, it would just be V1 plus V2. So the total voltage is the sum of the voltages in the resistors, or the elements. The formula or rule for current is that the current is the same everywhere in a series circuit. So no matter where you measure it, it's always the same, and so on. Now, they use the word REQ, which stands for equivalent resistance, and I like to use RT. So in some of these problems, I might end up writing RT. But R total or R equivalent is the resistance of the whole circuit taken at once, and that is equal to the sum of the resistors. R2 plus R3 plus so on for each of the resistors. So you can see these formulas right here, and they give you them not in the same order, but you don't have to memorize them. So let's go ahead and solve a circuit. So we have a circuit here. We'll label our battery plus and minus, and let's say it's a 24 volt power supply, and each of the resistors are 4 ohms, 3 ohms, and 5 ohms. So let's solve for the current and the voltage in every single place in the circuit. So the first thing that we can do is find the equivalent resistance. So we say Req is equal to R1 plus R2 plus R3. So this is pretty simple. We just sum them up, 4 ohms plus 3 ohms plus 5 ohms, and that gives us an equivalent resistance of 12 ohms. What does that mean? It means that this circuit is the equivalent of one resistor of 12 ohms. Now, we know how to solve one of those because we can just use VIR, V equals IR. So the total voltage, 24 volts, is applied to a total resistance of 12 ohms. So the current flowing through the resistor has to be 2 amps. So we know that the total resistance, Req, is 12 ohms, and we know that the total current is 2 amps. And what does the current rule say? That the current must be the same everywhere. So it's 2 amps in the battery, but it's also 2 amps here, 2 amps here, and 2 amps here. And in fact, it's also 2 amps in the wires because it's the same everywhere. Now, using VIR, we can do V equals I times R. So that would give us 8 volts, and 3 times 2, that would give us 6 volts, and 5 plus 2, that would give us 10 volts. So let's look at what the voltage rule says. It says that the total must equal the sum of all the 3 voltages. So 8 plus 6 plus 10, what does that give us? That gives us 24, so we know that we solved the circuit correctly. So let's go ahead and find the power in the 4 ohm resistor. So remember that they sometimes can say this as the rate of energy expended. That's another way of asking this question. What is it? W over T? Well, that's power. So we can do this most easily by saying P equals VI, and we're given the voltage in the 4 ohm resistor is 8 volts, and the current is 2 amps. So P equals 8 times 2, that would be 16 watts. Let's look at changing the number of resistors in a circuit. So we're going to deal with series circuits still. And let's say we have a 12 volt battery and we have 2 resistors, and each of those resistors are 3 ohms. And then what we're going to do is we're going to add a resistor, and we're going to see what happens to that resistance. So we know that the formula for resistance for the total is to add them up. So all we have to do is add 3 plus 3. So our equivalent resistance is 6 ohms. Now, using VIR, V equals IR, we can take the 12 volts divided by the 6 and find out the current is 2 amps. That means the current is 2 amps here, 2 amps here, and 2 amps here. But if we add another resistor, we increase the total resistance. So now, let's say we have 3 ohms, 3 ohms, and we added another 3 ohms. Well, now our equivalent resistance is 9 ohms. So now, applying VIR, V equals IR, we divide V by 9, the 12 by 9, and that gives us a current of 1.3 amps. That should make sense. The 12 is the push. The push hasn't changed, but it's more difficult to push through 9 ohms than it is through 6 ohms, so the current is slower here. It's not flowing as rapidly. Now, we can take this and redraw this as a single circuit that has a resistance of 6 ohms, because this is the equivalent. It's the equivalent. 2 3 ohm resistors in series is the same as 1 6 ohm resistor. And the other circuit we can actually represent as a circuit with an equivalent resistance of 9 ohms because it's acting as only 1. Now let's look at the rules for parallel circuits. Now these switch up. So this time the total voltage is equal to the voltage everywhere in the circuit. So before in series they added up, now they're equal. Before in a series circuit the current was the same everywhere. In a parallel circuit the total current is equal to the sum. So it's the opposite of what we did for a series circuit. Whoops, that should be a plus. And then the rule for resistance is tricky. It is a reciprocal rule. So it's 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3 and so on. So our parallel circuit rules are right here, so you don't need to memorize them. All right, let's go ahead and solve for a parallel circuit. So we don't know anything about the voltage in the circuit. They give us the current and the resistance in the first resistor, and then they give us the resistance in the second circuit resistor. So let's go ahead and figure out all of the missing pieces here. We can do that most easily by starting with Ver, and we know that V is equal to 2 amps times 20 ohms. That's for these right here. So our voltage is equal to 40 volts. Now, if it's 40 volts here, we can fill that in as 40 volts. But remember that the voltage rule says that the voltages have to be equal everywhere. So that means the voltage on this battery right here, the total, is also 40, and down here it's 40. So we can again apply Ver, and that gives us, let's see, 40 volts is equal to I times 5 ohms. So our current is equal to 8 amps. And we can do the totals up here because we know that the currents must add up. So if this is 8 amps and this is 2 amps, the current rule says add up the currents to get the total current. So what do we have here? We have 2 plus 8, so the total must be equal to 10. So we have 10 amps. So we can do Ver one more time and say that we have 40 volts is equal to 10 amps times R is what we're solving for. So R comes out to 4 ohms. Now, there's a way that we can verify this to show that this 4 ohms is actually the resistance up here. And we can do that by applying our resistance rule, which is tricky, and I'll show you how to do it. 1 over Req equals 1 over R1 plus 1 over R2. We only have 2 resistors. So that's going to be 1 over Req is equal to 1 over 20 ohms plus 1 over 5 ohms. Now, how do you do that on your calculator? So the way that you do that is you're going to use the x to the minus 1 button, because that's the reciprocal. X to the minus 1 is the same as 1 over x. So what we can do is say 20x to the minus 1 plus 5x to the minus 1, and that gives us an answer. But that's not Req. That's 1 over Req. Because we've summed these up, that's not Req, that's 1 over. So we have to hit x to the minus 1 one last time and hit enter, and that gives us 4. So our Req is 4 ohms, and that is basically not necessary, but it's a check that we did the circuit correctly. So lastly, let's say that the circuit was run for 1 minute, and they ask us, what is the energy consumed in the 5 ohm resistor? Well, all we have to do that is to look at our information in the 5 ohm resistor. So we know from our reference table that energy is equal to V squared over R times T. So we know the voltage is 40 volts. It's the same everywhere. over our resistance. Our resistor is 5 ohms, times the time, 1 minute is 60 seconds. And then we just do the math on that, and we get 1.9 times 10 to the 4th joules. This is counterintuitive, and it's a common question. Let's say we have a circuit, it's parallel because there's junctions, and we have two 10 ohm resistors in parallel. And the question is, if we add an additional resistor in parallel, what happens to the total resistance? Now, it sounds like more resistors, and then that would be more resistance, but it's not. More resistors gives us more paths, more options. So therefore, because we have junctions, we have other ways to go. An additional resistor actually makes the total resistance go down. So if we do 1 over Req equals 1 over R1 plus 1 over R2, and we put our numbers in, so we have 1 over Req equals 1 over 10 ohms plus 1 over 10 ohms. Then we do our x to the minus 1 buttons, and I would recommend trying this. You can pause the video and make sure you know how to do this rule because it's tricky. And when you do that, you get 5 ohms. But if we do this for the second circuit, now we have 1 over R1 plus 1 over R2 plus 1 over R3. So what's that going to give us for our Req? Well, that's 1 over 10 ohms plus 1 over 10 ohms plus 1 over 10 ohms. And when you do that, you get an Req of 3.3 ohms. Now, because the voltage is the same everywhere in here, there's going to be more current flow total in this circuit because there's lower resistance. So we can say that that first resistor, or that first circuit, I should say, is the same or the equivalent of one circuit. I didn't give a voltage. One circuit with 5 ohms, and the second one would be exactly the same as a circuit with one resistor of 3.3 ohms. That's why it's called equivalent resistance. This style of question comes up a lot, and the way it's asked is they'll say, here's 4 different circuits. Which two have the same equivalent resistance? And unfortunately, it's kind of a pain because the only way to do it is to solve for the equivalent resistance of every single one. So for the first one, I'm not going to redo it because we've done this multiple times. It's going to be 1 over 2 plus 1 over 2. Then hit your x to the minus 1 button one more time. And if you do that, you get an equivalent resistance of 1 ohm. This one right here is in series, so the resistances just add up. So Req is equal to 2 ohms. This one is only one resistor, so what's the equivalent resistor of a single resistor? That would be 1 ohm. And for this one, we would again do 1 over 1 plus 1 over 1, and then x to the minus 1, which gives us 0.5 ohms. So the answer to the question, which of these would have the same equivalent resistance, would be this one and this one. Measuring devices. How do we measure current and voltage? So in a real circuit, we need to take some type of device and measure current and voltage. In the old days, there were voltmeters and ammeters that were separate devices. But now, there is a device called a multimeter, and it has a little screen readout, and it has a dial, and you can switch that dial to measure current and you can measure voltage. And then there are 2 lead points that you can take and connect wires to them, and then take those wires and put them into the circuit. But there's different ways we have to wire them to make sure they work correctly. First off, the symbol for a voltmeter is a V, and that makes sense. So what is a voltmeter? Well, a voltmeter is nothing more than a device that does what? It's a device that measures voltage. Now, there is an added thing that you need to memorize, and that is that they must be wired in parallel. If you don't, it will not work. In fact, you will end up, when it's an ammeter, if you wire it wrong, you'll blow the ammeter. So this just won't work. So what is the other device? It measures current, but they use the letter A for amps, and that's called an ammeter. And what is that? It's nothing more than a device that measures, well, what would it measure? A lot of people say it measures amps, but it measures current in amps. And these must be wired in series. So let's go ahead and look at some practical ways that we would actually wire this. So the actual true way that you would do this, if you had your voltmeter, is you would connect one of the leads to one side of the battery and one to the other side. But we're not going to do that. We're going to do a circuit diagram. So what that looks like is you take a wire, you draw it around, put in your V, and do that. Now, what's this voltmeter going to read? Well, it's going to read the battery. And what is the battery? The battery is the total. So this voltmeter would read the total. Now down here in the individuals, we can put a voltmeter around this particular resistor and get the voltage of that resistor. You can also put voltmeters around two resistors at once, and that will read the voltage of both. But ammeters need to be wired in series. So we have to disconnect our wires and put our A in here. Because the ammeter, all of the current has to run through the ammeter to get to the other side. This would register the total current, and it really doesn't matter where we wire an ammeter in a series circuit, because ammeters are going to read the same thing. Because what's the current in a series circuit? Well, the rule is that the current stays the same, so these three ammeters would read different values. Now that's different from the voltmeters, because the voltage here plus the voltage of these two would add up to our total voltage here. So here's a question that you might get asked. They give you a circuit. They'll ask you to find some things, like in this case we're going to find the current and the voltage in the 4 ohm resistor, and then they're going to ask us to wire a voltmeter and an ammeter so that they could determine those in an actual reading. So we know that this is a series circuit, so we know the resistances add up, so that's 6 ohms with a total of 12 volts, so we can do VER. And VER would give us 12 volts is equal to I times R, which is 6 ohms. So our I is 2 amps. So we know that this would be 2 amps, 2 amps, and 2 amps. Now, we're only concerned with this reading, so we can do VER again. And VER is going to give us V equals, and that's going to be 2 amps times 4 ohms. So our voltage is going to be 8 volts. So that's 8 volts down here. And then it says wire in our voltmeter. So we're going to put our voltmeter around the resistor. It could also go on the bottom, but I have some numbers here, so I put it above. And we can wire our ammeter anywhere because the current is the same everywhere. 2 amps, 2 amps, 2 amps. So we have to erase the line here and draw our ammeter in like that. So what do voltmeters in a parallel circuit look like? Well, it's the same idea. Voltmeters must be wired in parallel, so we can put this around. But if we put this around this resistor, remember, voltages in a parallel circuit are equal. So we don't need to do this. We can only put in 1 voltmeter and we'll have the reading for every single one because they're all the same. Ammeters are a little bit more tricky. If we put an ammeter, remember, ammeters must be wired in series. If we put an ammeter here, it's going to read the total. When it gets down to here, there's a split. So if we put an ammeter in here, and it wouldn't matter, we could also put it on this side over here, and then we put another ammeter in here, remember the current has to add up. So the current coming in here, I1, would then split, and then we would have I2 and I3. So what would I1 equal? Well, that would be the sum of I2 plus I3, or we could say the sum of the readings in the ammeters. Kirchhoff's junction rule is actually pretty straightforward. It's the idea of conservation of charge. And what it says is that all the current that flows into a junction, and that's the key word here, into the junction, must equal all of the current that flows out of the junction. So what does that mean? Well, let's look at an actual example. Let's say we have a junction here, and we have 5 amps flowing in, 20 amps flowing out, and 3 amps flowing in. What's the reading in this ammeter going to be? Well, the way that I like to do this is just to make a little chart and compare the in to the out. What's flowing in? 5 and 3. So we can say 5 amps and 3 amps are flowing in. And we have 20 amps flowing out. So what are we missing? Well, we only have 8 on this side, so we're missing 12 flowing in. So that tells us that this reading right here is our missing 12 amps, and we know it's flowing in. So 12, 5, and 3 flow in, and 20 flow out. Let's apply this to an actual circuit. So here we have a circuit and we have a junction here. This is reading the total current. This is reading the current in this resistor, and this is reading the current in this resistor. So to do it, we can start out with some Ver, and we can say that we have 20 volts is equal to, because we know this has to be 20 and 20 because voltages in a parallel circuit are equal everywhere, equals I times R, and our R is 5 ohms. So we know that our current in, we'll call that I2, is equal to 4 amps. So that's the reading right there, 4 amps. And then to get it for this one, we can do Ver again. This time it's 20 volts equals I times 2 ohms. So our current, we'll call I3, is going to be equal to 10 amps. And now we can redraw this circuit. And we know that I3 is 10 amps going down, and we have 4 amps flowing to the left. So we have 4 flowing out, 10 flowing out. That means we have to have 14 flowing in. And that should make sense because what does our rule say? Our rule says that the total current is equal to the sum of the individuals. So 10 plus 4 is 14. It adds up. A fuse is represented by a symbol that looks like this. It's a circle with a little squiggle line, kind of like the Pepsi logo. And this is actually not on the reference table. However, the concept of the fuse is on the region, so you do need to understand this idea. And what is a fuse? All it is a device used to protect the circuit from overheating. Now, fuses aren't used that much anymore in homes. They're used in a lot of electrical appliances, and especially in cars. But in the home itself, we usually use circuit breakers, and they serve the same purpose, but they operate differently. And the way a fuse works is you have a circuit, and let's say that the max current that this resistor can handle before overheating is 3 amps. So in other words, this might be a television, it might be a light bulb, it could be anything. And if it reaches 3 amps of current, it's going to overheat. So we don't want that to happen, because if there's a surge of electricity, that could end up damaging our device. So what we do is we put a fuse in series with that device, and we have the fuse set to 2.8 amps. That means that if the current rises to 2.8 amps, the fuse burns out. And if the fuse burns out, it prevents electrons from flowing through the device, and it saves the device. So the fuse burns out and not your expensive television. A circuit breaker works in a very similar way, and there are panels in your house that have a little door. It's a metal door usually. It opens up, and there's all these black switches. These switches, when too much current goes through them, the switch flips. And this happens when you have too much current, often when you plug in too many devices, and the current starts to go very high. And so what you do is you have to wait till the circuit cools down, and then you can flip the circuit back again. So there's another device that you need to know about, and this one is on the reference table. It's called a variable resistor. Another name for that is a rheostat, but it's also the switch on your wall that dims the light. So some people call it a dimmer, but the Regents uses the term variable resistor. And it's a device used to change the resistance of a circuit. So what it is a coil of wires that have resistance. And then there's a contact point. And this contact point can be moved right or left. So if we move the contact point over to the left, over here, we end up with forcing the electrons to go through more of the resistor, so we can make it higher resistance. If we do the opposite of that, and we put it so that it's in contact down here, it only has to go through a little bit of resistance. So we can increase and decrease the resistance. Well, think about this. If we decrease the resistance, that allows more current to flow, so the light bulb will start to glow brighter. So you need to know this, and this is important, and you just have to memorize it, that power determines the brightness or the heat. So it's not current by itself. In a series circuit, it is current, but it's the power that determines how much the light bulb will glow and or how hot the element will get. So if we look at this, in this particular case, in a series circuit, because it changes in a parallel circuit, as the resistance goes down, the current goes up. And if we look at the formula P equals I squared R, if the resistor is fixed, it's a fixed resistor, fixed resistance, then as I starts to go up, the power goes up, so the light bulb will glow brighter. So this question is probably outside the scope of Regents, but I put questions like this on my test, so you should know how to do this, or at least the ideas behind it. Now, I drew resistors, but in this case, these resistors are going to be light bulbs, okay? Or we could say the heat of the resistor, either one. So the question is, which one's going to get the hottest? Or we could say which one's going to glow the brightest. So what we need to ask ourselves is which is going to have the most amount of power. And the way that we wire these changes the result. So in both cases we have 30 volts, and we have a 10 ohm and 5 ohm in series, and a 10 ohm and a 5 ohm in parallel. So how are we going to get the power in each of these? Well, the easiest way to do that is to get the current. So we know that this is 30 volts total and 15 ohms total. So 30 divided by 15 gives us 2 amps. So we have 2 amps here and 2 amps here. So we can do our formula P equals I squared R. And by doing that, we have the same I's, but we have different R's. So in this case, in a series circuit, the resistor that has more resistance is the one that will glow brighter. Now, you can put the numbers in and do the math, but I already did it, and that's going to be, for the first one, the 10 ohm resistor, that's going to be 40 watts. And for the second resistor, that comes out to half as much, that's 20 watts. So this is 40 watts, and this is 20 watts. So again, in a series circuit, the higher resistor glows brighter. But in a parallel circuit, we get a very different result. We have 30 volts here. We know that the voltages are the same in both, so we have 30 and 30. So we can do P equals V squared over R and put our voltages in and our resistances. And if you do that, for P1, for the 10 ohm resistor, you get 90 watts, and for the second one, you get 180 watts. So this is our 90 watts, and this is our 180 watts. So this is counterintuitive, because now the lower resistance one is getting the higher wattage. The 5 ohm will glow the brightest. So this is our brightest. This is our second brightest, this is our third, and then the least bright would be this.